here to talk about utilizing reduced build insulation concepts in the design of systems for large motors. And the way our paper is structured is we're going to review some of the activities that took place in the tests that were done in the development of the generator system, the reduced build system, and then talk about the migration of these concepts into the large motor arena, and give some of the preliminary results that we observed there. To start, we would like to talk a little bit about why one would operate an insulation system at increased electrical stress. We have to remember that to an electrical designer, insulation is actually a necessary waste space. If you can eliminate some of that insulation, you'll end up with increased efficiency in your machine. You can have increased uprates if you're rewinding machines. Or if you're designing rather new machines, you can make the new machines smaller. And at the same time, you'll have improved heat transfer between the copper and the core of the machine. Okay. The impact on the machine of a 20% reduction in insulation thickness is that the new machine cost is reduced in the order of 5 to 15%. We can increase generator uprates by as much as 15%, and we can have an increased efficiency for the machine due to a decreased loss in the order of 5 to 8%. That's the impact of a 20% reduction. Some of the design criteria that were used is that we knew that the new insulation system must offer the exact same reliability or better reliability than the old system. The new system must cost about the same as the old system, and when we say that, what we mean is the cost of a coil or a bar should be about the same as it was for the older system. And the new system must meet or exceed the old system test performance. One of the things that's worth talking about is that we observed that increased insulation stress cannot be accomplished by using standard materials and just simply reducing the insulation build. It is absolutely essential that you have corona-enhanced materials to be able to do this, and other factors as well, such as looking at the electrical stress distribution within the system. As a summary again, when we developed the hydro system, for stator bars, some of the things that we tested were the resin reactivity when we used the corona-resistant fillers within the material. We did material evaluations. We did tests such as DF tip-up and high pot on finished samples. We did voltage endurance testing to IEEE 1043. We did thermal cycling testing to IEEE 1310. And then we did mechanical bond tests and multi-factor stress tests as well. Sort of the fundamental thing that one needs to consider when they start to design a reduced build insulation system is what happens to the electrical stress within a coil or a bar. As you can see over on the slide here, that within the corner of the bar, what we're actually looking at is the insulation going around the corner of a stator bar. And when you do that, we look at the electrical distribution, and we'll note that right at the very corner of the bar, the electrical stress is approximately double the nominal stress. And so not only do you need to be examining this to determine where you need the corona resistance, but you also need to start to understand how to manage that electrical stress and to reduce it to be able to achieve decent life and reliability. I'd like to talk for a moment about some of the roadblocks that we had to overcome to get the generator system in place. The end grading system was the primary roadblock that we had to overcome. When we just took the standard end grading system, as you can see in the diagram or in the photograph, and we increased the stress on the insulation, we also increased the leakage current through the grading system, which caused overheating. And you'll see the sample on the right-hand side of the photograph, how it's quite brown in the area, especially at the junction. And this is because of increased heating. So we needed to completely redesign the way that we did the grading system to eliminate that problem. The photograph that we show here is showing a stator bar sample sitting in an Instron. And what we do is we would pull on the copper until we broke the bond between the insulation and the bare stator bar. And what we found was that a well-made system, to break that bond, you actually have to physically yield the copper. So you physically have to stretch the copper to be able to break the bond. And we had that both at room temperature and at elevated temperature, and it's the same for both standard stator bars and stator bars using the compact build insulation. And that was a summary of the work that was done in the past, and now the question would be the application in motors, and why would we do that? Now this can be best summarized in the table that's shown right here beside. And what you can see in the table is that if we were able to reduce the insulation build by 20% within a motor, we could achieve a machine with a reduced D squared L, which is a rough measure of the volume of the machine, in the order of 20 to 40%. Or if you just took that and translated that into machine weight, you could see a reduction in the order of 12 to 60% in the machine weight, which is an incredible number. It would be absolutely amazing to be able to do that. Even if we didn't achieve the 20% reduction, anything that we could achieve would give us a very large number for reduction. And so that's the whole motivation behind it. We thought that it was very exciting when we did it for hydro generators, but it's even more exciting, particularly for induction machines. The work that we have ongoing right now is looking also at voltage endurance, which is the fundamental principle, or one of the fundamental tests rather, that has to be done on an insulation system. And here we show a photograph of coil samples which were made for large motors, and they're on voltage endurance. Interestingly, when voltage endurance is done on large motors, it's done at 155 degrees C versus the 110 or 120 at which we do testing for hydro generators. This graph shows the results which have been observed to date for the insulation system. Now what we have here is actually we started doing testing on the turn package of the insulation system, knowing that based on the graph that I showed earlier, the stress distribution, anything that's close to the copper is going to experience a higher electrical stress. So we know that if we manage that portion of the insulation correctly, we stand a better chance of achieving success for the overall system. Now here what you'll see is that the corona-resistant turn tape is significantly improved as far as voltage endurance life over either of the two approved vendors that we currently use for the motor system. So the voltage endurance is improved. Next we'll talk about the thermal evaluation. This is an interesting test, and this is a test which is not performed at all for hydro generators. I'm not completely sure why, because it seems like a very good test. The photograph here shows the facility that is used for doing the test. You start with 3 different temperatures, so you can see the 3 different ovens in the background, the green ovens that are there, and you accelerate life by aging at higher temperatures, and after a prescribed period, a motorette, which is a small stator I'll show a picture of next, is taken from the oven, put onto a shaker table where it is shaken, then it's taken into a 100% humidity chamber, which is shown in the forefront, and after being in there for a prescribed period, it's given a high pot test. If the samples pass, they continue to go through the testing until all the samples fail. Okay, so this is a very good test for determining the thermal rating for an insulation system. This next photograph shows what the Formettes actually look like sitting in the oven. You can see that they're a mocked up stator. They have approximately 3 or 4 coils in each one, and each coil leg is tested individually until it fails. Now, the test results observed are compared for the compact system and the standard system, and what you see is that the compact system actually yields a longer life based at 155 degrees C, even though both systems give about the same 20,000 hour life at approximately 180 degrees C. So you can, and this testing is all done in accordance with IEEE 275 or 429. They're very similar tests. Okay, so what we see is that the Formette evaluation gave characteristics for each system that have a different slope. And I think any system that you have, as you change that system, you'll have a characteristic curve for that system. And also the compact system gives longer life test on as far as the thermal classification at 155 than the regular system. Another test that was performed on the compact motor system, which is not performed on hydro generators, is a different form of thermal cycling test. As opposed to being done per IEEE 1310, which is done in free air with the sample sitting out, this is done in a Formette. And the intent is to simulate a hard start in a motor so that the samples are heated very quickly and then cooled down more slowly. And what you see is the Formette fixtures, you get a really close look at them, even closer than we saw when they were in the Formette test. They're hooked up to a high current source and are then heated. Okay, the results for this, this testing is that these stators have undergone 15,000 cycles. The 1310 samples typically will go through 500 cycles. Well, in this case, they went through 15,000 cycles where they were heated from 40 degrees C to 120 degrees C in 20 seconds. So a very fast temperature rise. Now, of course, it took longer to cool them because it's forced air cooled. And then you trend the DF, the capacitance, and the partial discharge and plot that all versus the number of cycles. And what we found was that we got very similar results to the other thermal cycling test, probably because of the superior bond, but the trending showed that there was very little deterioration in the characteristics over time. Another area of concern, which is more particular to motors than to generators, is the application of variable speed drives. Turn-to-turn insulation is noted for having problems when the motor is hooked up to a variable speed drive because of the repetitive pulses that come from the drive. And we know based on our experience that when we enhance the corona resistance of an insulation system, we make the motor more robust to those pulses that are coming in from the variable speed drive. One of the things that's helping us to do is that in the past what we've done when we know that a motor is going to go on a variable speed drive, we've always increased the turn insulation thickness to help to protect it from the surges. But we know right now as well that at the same time that we do that, the turn insulation also acts as ground wall insulation, so we don't need to, we can actually decrease the amount of ground wall to compensate for the increased turn insulation to help to fit it in the same slot. And also we know that if we can increase the corona resistance of both of those insulations, we can still thin the overall system down as well. The biggest single issue that we have, more so in the motor area than in the generator area, is that there's going to be manufacturing issues. Many motors are designed to operate at 4 kV. They have very thin insulation builds, and trying to take 20% out of something that's very thin is difficult to do. We feel that the biggest limiting factor is going to be the mechanical abrasion that the coils will have to withstand. So we know that this can be a problem for low voltage machines. We also know that to get there, we believe that we need to continue to use the corona resistant strand insulation. And again, issues like tape lay, tensioning, indexing are all the more critical when it comes to thinner builds because there's less insulation, so you can't tolerate those things as well as you could when you use more insulation. One of the other interesting things that we observed is that when we did the voltage endurance tests, it became apparent to us that even on reduced or low voltage machines, we'll probably need to use conducting armor instead of regular armor. Trying to combat some of these issues, as we developed this system, we actually built a partial stator and had the winders try and wind these because it's going to become absolutely imperative that the winders learn new practices and become better at winding machines so that we don't have problems in the future. Okay, in summary, the patented compact systems being manufactured for generator designs are out there. We're using them. Similar filled material technology is being leveraged in the areas of large motors. Compact build technology can yield significant motor component savings. Design size can be reduced for any new rotating machine by using compact builds. Filled material concepts can improve the problems associated with variable speed drives. And lastly, at the present time, compact designs are being developed for large motors and are also being quoted at some voltage ranges. Okay. Thank you.